The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Astronomy has made amazing strides thanks to the James Webb Space Telescope, which provides a previously unattainable view into the deepest and most remote regions of the cosmos. Scientists and the general public have long been captivated by Pluto, a minor planet that is the subject of one of the most important and unexpected recent discoveries. What was formerly believed to be a frigid, desolate world at the fringe of our solar system has proven to be considerably more fascinating than initially thought. The James Webb Telescope has uncovered startling new information about Pluto that is fundamentally altering our understanding of this far-off planet. Before being downgraded to a dwarf planet in 2006, Pluto was ranked as the 9th planet in our solar system. Since then, spacecraft like NASA's New Horizons, which made a flyby in 2015, and now the James Webb Telescope have contributed significantly to our understanding of Pluto. Prior to the James Webb Telescope's launch, Earth-based telescopes were used for the majority of Pluto studies, although they were limited in their ability to record details. NASA had long assumed that Pluto was hiding more secrets than it was willing to admit, but what James Webb found dramatically supported those theories. Scientists have been anxious to investigate Pluto's surface, atmosphere, and the hidden intricacies of its moons ever since the James Webb Space Telescope trained its powerful lenses on the planet. By using infrared equipment, the James Webb spacecraft can see characteristics that were previously hidden behind Pluto's clouds and frozen atmosphere. Beyond Pluto's icy, far-off surface, scientists discovered a much more sophisticated structure than they had ever expected. The finding that Pluto appears to have an underground ocean beneath its ice surface was among the most astounding. It was previously believed that Pluto was a frozen world too frigid to support liquid water. Nonetheless, the information gathered by James Webb implies that Pluto's core generates heat, keeping a subterranean ocean liquid. This finding may significantly alter our perception of potential life locations in the cosmos. One of the necessary components of life as we know it is liquid water, and the prospect that Pluto may have subsurface life has rekindled interest in the quest for alien life. The topic of Pluto's subterranean ocean existence also calls into question Pluto's geological processes. Pluto doesn't seem to be a dead planet. Instead, it seems to be experiencing tectonic movements and cryovolcanism, volcanic activity that spews icy forms of water, ammonia, or methane instead of molten rock. The discovery by James Webb of what seem to be cryovolcanoes on Pluto's surface raises the possibility that the dwarf planet occasionally sees ice material explode from its interior. Such activity suggests that the globe is far from static, with forces operating beneath its surface that are constantly reshaping its terrain. A significant finding from the James Webb observations is the intricate atmosphere around Pluto. Although Pluto's atmosphere was previously identified by the New Horizons mission, significantly more precise details regarding its makeup and characteristics have been revealed by the James Webb Telescope. Despite its thinness, Pluto's atmosphere appears to fluctuate significantly based on where it is in its extended orbit around the Sun. Pluto's atmosphere vaporizes when it gets closer to the Sun, but freezes and falls to the surface as it moves farther away. This sublimation process is far more dynamic than previously believed. Furthermore, unexpected gases in Pluto's atmosphere have been discovered by James Webb's infrared capabilities. These gases may include residues of organic molecules created by biological or chemical activities in the atmosphere. Pluto's atmosphere contains organic chemicals, which raises more questions about the potential for life on this far-off planet. The basic building blocks of life are organic molecules. Although the precise makeup of these substances is still being investigated, their existence begs intriguing questions regarding whether or not rudimentary life forms have ever lived on Pluto. Could life exist in the icy, hostile environment beneath Pluto's surface? Although it is too soon to provide a conclusive response, the discovery of organic chemicals raises intriguing possibilities regarding the existence of a subterranean ocean. It has also become clear that Pluto's surface is significantly more diverse than originally thought. High-resolution photos taken by James Webb reveal a highly varied terrain. Huge expanses of nitrogen ice blanket Pluto's surface, dotted with water ice mountains and enigmatic red areas that scientists surmise may be tholin deposits, complex organic compounds produced when methane interacts with cosmic rays or ultraviolet light. These tholin deposits may include information on the chemical activities occurring on Pluto and could even bear similarities to the primordial chemistry that existed on Earth before the emergence of life. Along with these findings, there is now a revived interest in Pluto's moons. It was originally believed that Pluto's largest moon, Charon, was geologically dormant. However, James Webb has noticed indications of recent tectonic activity. Large cracks and canyons on Charon's surface suggest that internal heating may have occurred there at some point in its past. This raises the question of whether, like Pluto, Charon may have a subterranean ocean, although the evidence is not as strong in this case. However, the possibility that liquid water may be present beneath the surfaces of both Pluto and its moon has sparked intense astrobiological study in the once peaceful outer regions of the solar system. The orbital dynamics between Pluto and its moons remain one of the most mysterious aspects of this system. James Webb's investigations have shed fresh light on their interactions. Some of Pluto's smaller moons, for example, seem to have chaotic orbits, tumbling unpredictably through space. The intricate gravitational interactions between Pluto and its 5 moons are likely responsible for this phenomenon. Since Pluto and its moons are believed to be remnants of the Kuiper Belt, a region of space filled with frozen bodies left over from the solar system's formation, studying these dynamics might provide crucial insights into the early history of the solar system. One of the most pressing questions arising from these discoveries is what they mean for the future of space exploration. Pluto and its moons appear to be much more than lifeless, frigid remnants of the solar system's ancient past. Rather, they are dynamic worlds with complex atmospheres, active geological processes, and perhaps even conditions that could support life. This suggests that other distant objects in the Kuiper Belt, and possibly beyond, may also hold surprising secrets. Furthermore, the discovery of a subterranean ocean on Pluto influences the search for extraterrestrial life. Traditionally, habitable zones, the regions around stars where liquid water can exist on a planet's surface, have been the primary focus of these searches. However, Pluto is well beyond this zone, yet it appears to have conditions that allow liquid water to exist beneath its surface. This implies that liquid water, and possibly even life, could be present on other frozen worlds, even those far from their parent stars. Scientists may now be more inclined to investigate other minor planets and moons in the outer solar system, such as Europa, Enceladus, and Triton, all of which are believed to contain subterranean seas. In light of Pluto's findings, these discoveries could have implications far beyond our solar system. If Pluto, a tiny, icy world, can have an active geology, a complex atmosphere, and possibly even an ocean, then similar conditions could exist elsewhere. The Kuiper Belt, where Pluto resides, is just one example of a region filled with small, frozen worlds. It is likely that many other star systems have Kuiper Belt-like regions with objects that are just as active and surprising. One day, the James Webb Space Telescope may discover habitable planets around distant stars, opening new pathways for the search for extraterrestrial life. The discoveries on Pluto highlight the importance of continued investment in space exploration and technology. As we push the boundaries of what we can perceive, Pluto, once thought to be a forgotten world at the solar system's edge, has become a focal point of scientific discovery. It serves as a reminder that even the most distant objects in space may hold clues to the greatest mysteries of the universe. Methane and carbon monoxide are present in minute amounts in Pluto's atmosphere. The James Webb Space Telescope has found evidence of more sophisticated organic compounds. These molecules may be created by photolysis, the process of sunlight interacting with Pluto's surface ice, or by cosmic rays interacting with Pluto's atmosphere. These substances are interesting because they are frequently intermediates in more sophisticated organic chemistry, the type that might potentially result in nucleotides or amino acids, the building blocks of life. Additionally, these findings imply that Pluto's atmosphere is significantly more dynamic than previously believed. Pluto has dramatic seasonal variation while it travels along its 248-year elliptical orbit. Its atmosphere grows when surface ice sublimates into gas at its closest point to the Sun. This atmosphere then condenses and freezes back onto the surface as Pluto moves further away. The results from James Webb suggest that these processes may not be as simple as previously thought, possibly due to Pluto's distinct geology and interior heat. Complicated interactions between the surface and atmosphere appear to be occurring as Pluto moves away from the Sun, rather than experiencing a simple progressive loss of atmosphere. These discoveries contribute to the increasing understanding that Pluto is a dynamic planet that is always changing rather than a straightforward, inert entity. Another topic of significant interest is how Pluto's moons, especially Charon, have shaped the ecosystem around the dwarf planet. With a mass around half that of Pluto, Charon has a strong gravitational pull on its parent planet. This interaction influences Pluto's atmosphere's behavior in addition to causing tidal heating that might maintain Pluto's interior ocean in a liquid condition. Pluto's atmosphere may be distorted by Charon's gravitational force, which might add to the unusual dynamics that James Webb has observed. Furthermore, Charon itself exhibits surface characteristics that suggest a history of tectonic movements and potentially cryovolcanism, indicating signs of geological activity. This raises the question of whether Charon, too, is capable of supporting a subterranean ocean and what that would mean for the possibility of moons in the outer solar system being habitable. New information about the history of Pluto and Charon has also been made possible by James Webb's investigations. Pluto's surface is cratered, a sign that it has been impacted by debris from the Kuiper Belt, an area beyond Neptune that is home to frozen planets and solar system leftovers from the early era. Nonetheless, several areas of Pluto, including the enormous expanses of nitrogen ice called Sputnik planitia, seem to be quite fresh and have few impact craters. This implies that Pluto has recently resurfaced, most likely as a result of tectonic or cryovolcanic events. Likewise, the fractured surface of Charon indicates a history of geological activity and interior heating. These findings suggest that Pluto and its moons are not ancient, unchanging objects, but rather active worlds that have evolved over billions of years. Understanding Pluto's geological and atmospheric mechanisms is essential to assembling the larger picture of the solar system's genesis and development. As one of the biggest objects in the Kuiper Belt, Pluto is believed to contain some of the solar system's oldest and most primordial material. Scientists can learn more about the early history of the solar system, including how planets formed and migrated to their current locations, by examining Pluto. New insights into the chemical makeup of Pluto's atmosphere and surface are being offered by the James Webb observations, which may help scientists understand the mechanisms that shaped not just Pluto, but also other Kuiper Belt objects. It also clarifies the broader question of how planets and their satellites interact, given the intricate relationship between Pluto, its moon, and the surrounding space environment. For example, Pluto and Charon have a unique gravitational connection in the solar system. Because of its size in comparison to Pluto, Charon and Pluto are frequently referred to as a twin dwarf planet system. Their tidal locking keeps both bodies facing the same way, influencing the geology and atmospheric dynamics of both. Scientists are learning more about the formation and evolution of these systems thanks to James Webb studies. This knowledge may have implications for our understanding of exoplanetary systems. The surprising information from Pluto has led scientists to reassess other ice worlds in the outer solar system. If Pluto, a planet long believed to be lifeless and frigid, can display such intricate activity, imagine what may be occurring on other objects in the Kuiper Belt or the moons of gas giants such as Neptune and Uranus. Scientists are now using the telescope to explore other distant objects, such as Triton, Neptune's largest moon, which is also believed to contain a subterranean ocean and a geologically active surface. James Webb's discovery of Pluto's hidden secrets has inspired scientists to employ the telescope for further research. These discoveries have the potential to transform our knowledge of the outer solar system and offer fresh opportunities in the search for life. One of the most exciting implications of James Webb's discoveries on Pluto is the possibility that the Kuiper Belt, and possibly even the Oort cloud beyond it, contains more dynamic worlds with complex geologies, atmospheres, and possibly even conditions necessary for life. Pluto is only one of many planets within the vast and largely unexplored Kuiper Belt. Scientists are starting to delve deeper than ever into this distant frontier thanks to James Webb's powerful instruments. As we continue to explore the farthest reaches of the solar system, we may uncover many more surprises. The findings on Pluto are only the tip of the iceberg. The discoveries made by James Webb have consequences that extend beyond our solar system. Pluto's dynamic geology, complex chemistry, and possible liquid water environment raise the possibility that exoplanets and exomoons in other star systems may be undergoing similar processes. Other small, frozen worlds orbiting distant stars may share characteristics with Pluto, allowing them to maintain geological activity and potentially even harbor liquid water. Scientists are already using the James Webb Space Telescope to explore exoplanets, and the insights from Pluto may help interpret the data these far-off worlds provide. Specifically, the discovery of organic chemicals in Pluto's atmosphere may serve as a model for detecting similar substances on exoplanets, which could be crucial in identifying the possibility of life. Traditionally, the search for extraterrestrial life has focused on Earth-like planets in their stars' habitable zones. However, Pluto's findings are shifting that perspective. If a small, frigid world at the edge of our solar system can support liquid water and complex chemistry, then other distant worlds, even those far from the warmth of their parent stars, may be able to support similar conditions. Using its cutting-edge instruments, the James Webb Space Telescope is poised to play a crucial role in studying exoplanetary atmospheres and surfaces in search of water, organic compounds, and other possible indicators of life. Furthermore, the discoveries made on Pluto are forcing scientists to reconsider existing theories about planetary formation and evolution. Pluto's dynamic geology and potential interior ocean suggest that even small bodies may retain enough heat to sustain major geological processes. This challenges the conventional wisdom that only large planets with dense atmospheres and strong gravity can sustain prolonged geological activity. If Pluto, a dwarf planet on the outer edge of our solar system, can maintain such activity, what other dynamic small worlds might exist in the cosmos? This suggests that planetary science models may need revision and has significant implications for our understanding of planetary and moon evolution. In addition to raising questions about Pluto's potential for life, the surprising discovery of a subterranean ocean provides crucial new insights into planetary geophysics. It was previously thought unlikely that a planet as distant from the Sun as Pluto could have an interior ocean. This contradicts existing theories about how planets retain heat and remain geologically active over billions of years. On Earth, internal heat is sustained through plate tectonics, radioactive decay, and the Sun's influence. Given Pluto's small size and extreme distance from the Sun, one would expect it to be geologically dead. However, James Webb's findings suggest the opposite. This has led to research into alternative mechanisms for heat retention in icy bodies. One theory is that tidal heating, caused by gravitational interactions between Pluto and Charon, generates heat. Their close orbit causes internal expansion and compression, which may be sufficient to prevent Pluto's subterranean waters from freezing completely. While moons like Europa and Enceladus have shown evidence of tidal heating before, finding such activity on Pluto was unexpected. Pluto's possible liquid water suggests that cryovolcanism, volcanic activity involving the eruption of volatile substances like water, ammonia, or methane instead of molten rock, may be reshaping its surface. If confirmed, this would revolutionize our understanding of geological activity on icy worlds at the edge of the solar system.